I'm going to make the recording available. I don't know when our Blackboard will come in, but I might just post a link where you can access it in case so you need to what we could go with this one. So how many of you are already here? Just want to make sure. Now there's only 1, 2, 3, 8 of you. All of you teaching chemistry? No? Why do you have this course if you're not teaching chemistry?
Professor, I think it was a matter of space because I'm going to be doing chemistry. I think some of us also doing chemistry while others are going to be teaching biology, which
I see.
it's going to be a living environment.
Most of the stuff that I have is about chem, especially the one for next meeting. So good thing you told me that not all of you, so at least I can make it like a general science thing.
Never bad to be well-rounded, right?
That's true, Ross.
Anyway, chemistry is that what they call the central science. So it touch base in almost other courses that we have. So what I'm going to do for the first part, just tell you about these so-called big ideas in chemistry, and then later on, so I was hoping that all of your chemistry, we're going to have some interactive session. I'll ask you first, maybe in some slides, to input what you thought about when we talk about this chemistry concept. And then later on, I'm going to give examples on how you're going to discuss, you have concepts in chemistry, the different concepts in chemistry. So that's the idea that I have for today's session, because as I have told you, okay, I'm going to meet you 3 times, including today, and these are the topics that we have. So for today, we're going to tackle about big ideas in chemistry. And then on Thursday, we're going to talk about strategies in teaching chemistry. And then next week, we talk about doing chemical analysis, because my specialization is on analytical chemistry. Okay, which I always use as the most practical chemistry among the fields of chemistry. So I'm Elmer Mojica. I'm an associate professor in the Department of Chemistry. So you can email me in this email ad, emojica. So the best way to remember this is Emoji California, okay, at pace.edu. Okay, so we're going to discuss today about the so-called big ideas, okay, of chemistry. So if I ask you what is chemistry, most likely, okay, this is the one that comes into your mind, okay, the science of matter and its transformation. So whenever we talk about chemistry, usually the word matter is synonym, what we call synonymous to it. So if you're going to look about what matter is, how do you answer the question about what is matter? Okay, so usually it is everything around us. So matter, as they said, is anything has mass and occupies space. Okay, so if you're going to look around us, almost all of them has mass and occupies space. So we could say matter is everything around us, or the stuff that is around us. So chemistry is the science of matter and its physical transformation. But if you're going to look at the history, okay, we could say that chemistry as a science has a I'm going to write this, pluralistic constitution, okay, that can be characterized along epistemological, ontological, methodological, and axiological dimensions. Okay, so we could say, if we're going to look at this chemistry discipline, it has a dual characteristic. It is both what? A natural science and technology. Okay, so if we're going to look about chemistry, there is more than one definition of this concept. And usually it depends on the so-called epistemological and sociological characteristic of chemistry. Okay, but the most common way to describe the word chemistry is the one written here in the slide. Okay, it can be, we could say, portrayed as a science of substances and processes, which is similar to the one that we have here. Okay, a science of substances and processes. So you just convert these to substances, and this one is what? Processes. So that's just one way of defining chemistry. Another way they could say it's a science of material transformation. Now the central idea is still here. Okay. Another one would say it is a central science, as I have told you earlier. Why is it a central science? Because if you're going to look at all the scientific field in one way or another, chemistry is there. Okay. Another what we call article define chemistry as an academic and industrial science. Okay. And then another one would say it's a practical science. So there's a lot of what we call definition of chemistry. That's why if you're going to look at the pluralistic approach, okay, if you're going to look at them, all of them just falls in this what we call definition. Okay. Now, if we're going to look at the so-called conceptual profile, okay, so when we say conceptual profile, this can be understood as models of the diversity of modes of thinking available to individual from a given socio-cultural context to use in different domains of their experience. Okay, so what does this conceptual profile means to us? So I don't know if you're familiar with the story of the 6 blind men and the elephant.
No.
Each of them describing the elephant based on the parts of the elephant that they touch. Okay, so the same thing we could say about the conceptual profile. Okay, so conceptual profile can be understood as the models of the diversity of modes of thinking available to individuals from a given socio-cultural context to use in different domains of their experience. So what does this mean? Each of these different modes, okay, of thinking corresponds to a zone in the conceptual profile of a concept. So each of the zone offers a way of understanding a concept, okay, that is different from the other set of zones. So if we're going to look at this chemistry conceptual profile, we can look at it like this one. Okay, so you have the monist zone, epistemic zone, processual zone, pragmatic zone, aversive zone, and attractive zone. So what does this mean? Okay, each of the zone has a different concept of the chemistry. So for instance, if we go to this what we call monist zone, so it treats chemistry as a natural science. So the question that can be asked in this zone is, what is the nature of the chemistry? How does chemistry evolve? So if you're going to look at the mode of thinking in the monist zone, chemistry is conceived as the essence of reality. So chemistry is all around us and everything is chemistry. So chemistry exists since the origin of the universe. Outside our consciousness, chemistry is omnipresent. Okay? So example ways of speaking, if you are in the morning zone, the essence of existence, all that we see, feel, or breathe, everything. Chemistry is made and is present since the creation of the universe. Okay? So that is the what we call conceptual profile if you look at it in terms of monisome. Okay. Now in the epistemic zone, so here the concept of the chemistry is just like of a multi-dimensional science. And question that you can ask here, what's the nature of the chemical knowledge? What does learning chemistry entail? Okay, so here in the epistemic zone, chemistry is conceived as a science, a systemic body of knowledge, a branch of scientific knowledge, a school subject, and chemistry is understood as a conceptual and theoretical framework. Okay, so example of way that you're speaking if you are in this zone, science that studies the transformation of matter, elementary constitution of compounds, molecular composition, geometry, and other what we call chemistry concepts. Okay? So you could see the different, we could say, concept that they have from a natural science, now it becomes a multi-dimensional science. Okay? And then we go to the other zone, the processual zone. So in the processual zone, this is what? The representational science. Okay? And here, we could say chemistry is conceived what? The root word itself. Okay? The process. So we can ask question here, what is the role of models in chemistry? How do chemical symbols support thinking? Okay, so we conceive chemistry here as a process, okay, or event that we could say involve specific entities. Okay, it is seen as a transformations, as chemical reactions that leads to certain products. Okay, so ways of speaking in this zone is reactions that may give rise or break down something. So chemistry is the interaction of events in order to get another result. Okay, so you can see each aspect of chemistry is being what we could utilize in this different zone. Okay, so from the natural science, multi-dimensional science, representational science. So in one way or another, they cover chemistry. Okay. Now, if we go to the other zone, so we have the pragmatic here. So this involves technoscience. So here, what are the aims of chemistry? How do chemical thinking and actions affect the world? So if we're going to look at this zone in terms of the mode of thinking, we could say chemistry is related to what? Practical, operational, and technological situations. So chemistry here is seen as a technoscience. So here in the dual nature of chemistry, we could say it's a technology. Okay, so chemistry here is seen as a technoscience, as an industrial enterprise, a career, or an activity carried out with a particular purpose. So if you're going to look at the way of the speaking here, think about the chemical industry, the scientist, okay, the professor, the course I'm thinking, and that I will work in this area later on. Okay. Now, the other aspect of what we call the conceptual profile is the aversive zone. So this is, we could say, the impure science. And unfortunately, we have a negative connotation or impression, not only of chemistry, but of course of the science right now. Why do you think a lot of people don't believe in vaccination? Okay. So if you're going to look at it, what is the public image of chemistry? How do we make chemistry relevant? Okay. So why do you think people don't accept the science when we talk about them? Because they cannot accept a process that is very imperfect. You know, science is not a perfect process. Okay. A good example in the pandemic that happened today. At the beginning, they said you don't have to wear masks. Now they said you have to wear masks. But if you're going to look at the reason why they told you not to wear masks at the beginning is because they don't want to run out of the supply that is needed by the medical field. Okay? So this is, we could say, a challenge that we as educators need to overcome for us to have a great impact in the society. So in the aversive zone, the mode of thinking that we have there is chemistry is related to something that is lethal, responsible for environmental pollution. Okay? All of us, when we mention the word chemical, it always have what? A negative image. But if you study chemistry, you know water is a chemical, right? But to an ordinary person, whenever you mention chemical, it is something that is not good. Okay? So this falls in this so-called aversive zone. So chemistry is associated with chemical products, right? What's the main connotation right now? Everyone wants to go to nature, what we call be natural. They don't want to do what we call the artificial stuff. Okay, so everyone wants to go with the so-called organic foods because the other what we call the materials are artificial. But if you're going to look at the process that happened, your body will not identify, let's say, a vitamin C as coming from citrus or from a vitamin C tablet. Okay, all it knows is if you're vitamin C, okay, you are good to the body. Or let's say, what's the other thing that they say? If it's artificial, it's always bad. If it's natural, it's always good. There are poisons that are natural. Cyanide coming from, let's say, cassava, okay? They are produced naturally, but they're still lethal. Okay, so this is the aversive zone of the conceptual profile of chemistry, and unfortunately, we can see them. Okay, now the last part that we have here, I make it the last part, that's the attractive zone. And here, chemistry serves as the central science. So chemistry is conceived as a feeling, as an attraction, affinity, a love. Okay, it is related to a strong connection between two people. So we could say here, being a central science, how does chemistry relate to other disciplines? How does the chemistry fits in the STEM education? So as I have told you, this conceptual profile that that we have, this is just similar to the I don't know what you call this, the fable, okay, of the 6 blind men and the elephant. So if you're going to see the slides here, one of the blind men said it's a fun because he touched the ear. One of says is what we call a spear because he touched what do you call that ivory tusk? Is it the ivory tusk that you have there? Okay. And then one said it's a snake because he touched the one here in front. One say it's a wall because he touched the main part of this. And then one who touched the pit says it's a tree. And the one who touched the tail says it's a rope. So in one way or another, they are right in describing the elephant, but that's not the overall description of the elephant. So that's how I want you to look at the conceptual profile of the chemistry. Now the question now as a teacher, okay? If you are a teacher, you're going to be asked, you're going to ask yourself what to teach in secondary schools and why teach it, okay? Answers to the question of what to teach in secondary school and why to teach is have been the subject of what? Debate for many years, okay? Question what content is relevant to teach is also, we could say, debated for years. For what purpose should this content be taught? And for whom should the content be relevant? Okay, or relevant. So if we're going to look at this set of questions here, the responses for this question often vary with the different stakeholders in science education. So who are the stakeholders? The teachers, the students, and sometimes the administrator. Okay. Now, the policy, or we could say the goals of the policy makers are not always aligned with those of educators. And what they aim and what they value is often different from what the students judge as relevant to them. Okay. In fact, many students find that the content of science education courses very interesting. They do not find the content of the science education very interesting, and they are not motivated to invest too much effort in these classes. Okay, so you have a bad, what we could say, stigma whenever it is STEM, whether chemistry, biology, and worse, math and physics. Okay, so if we're going to look at this, let's look at these so-called domains of relevance. Okay, because you as a teacher, you want to teach a course that you want your students to see it as a very relevant matter to them, okay, or a relevant course to them. However, if we're going to look at this, the way that you're going to teach this so-called relevance in terms of the domain, okay, these three domains of relevance, it came down, okay, from the three main goals of education. Anybody knows what's the three main goals of education? So when we get education, one of the things that we want to have is personal growth. So personal growth, this is what? Directed at stimulating students to shape their individual identity through growing experience in the cognitive, affective, and psychomotor domains. Okay? So out of this, what we call personal growth, if you're going to look at the domains of relevance, there's a domain of personal or chemistry relevance. So this domain, okay, encapsulate the aspirations that all students will experience the richness, and excitement of knowing. Okay, so this domain encapsulate that the aspiration that all students will experience the richness and excitement of knowing about and understanding the natural process, the natural world, and the use of appropriate scientific process and perspective in making personal decision. Okay, so what's the relevance of this domain? As much as possible, it is expected that chemistry education will enable students to consider chemistry as a particular way of examining the natural world, experience the interesting relationship between chemistry and technology because it deals okay, with concrete objects from their everyday life. Understand the applications of chemistry in their daily life and value, okay, aesthetic aspect of chemistry phenomena for personal satisfaction. So in this domain, we want our student to have a personal growth, which is one main goals of education. Okay. Now, what's the other main goals of education as related to the next one? Socialization.
Get get people to behave in ways that they usually don't behave.
Okay. So, what's the main problem if you homeschool your children? Okay. What's the main problem in the pandemic that happened this year?
Lack of social interaction.
Yeah, lack of social interaction. Because one main goal of education is socialization. The goal of socialization, and this is focused on preparing students to become responsible citizens through learning of social rules, okay, accepting social rules, and acquiring skills that are required for fruitful interactions with other people in society. Now, there is a domain of relevance for that in chemistry. So the domain of the societal or chemistry relevance. Okay? So this domain encapsulates the aspirations that all students will engage intelligently in public discourse and debate about matters, okay, of scientific and technological concern. But unfortunately, I think the socialization right now is really what? Extreme. If you're going to look at the socialization in terms of the aspect of the mass, you could see the difference there. Okay? But what you're trying to do here in terms of chemistry, in terms of the domain of societal relevance, is the education or the chemical education will enable students to understand the historical influence of chemistry on society, okay? Be informed citizens who are prepared to deal with chemistry-related societal issues to vote responsibly and to influence when appropriate policies related to the impact of chemistry on society, to critically follow discussions about chemistry in popular media, and be citizens who have positive attitude toward chemistry. So the question now, was this domain inculcated successfully to our students? Okay? Because from the way I look at it, just looking at the news right now, I think science, unfortunately, is not as strong in this country compared to the other country. Okay? You want to see the proof? You watch the news. Until now, a lot of people still don't believe the use of mass. Okay? So that we could say the societal relevance and how it is, we could say, related to the three main goals of education. Now, the last main goals of education after personal growth, socialization, okay, the last one is the goal of qualification. So the goal of qualification is directed at preparing students for employment in fields that best fit their interests, ambition, and abilities. So here, this is the domain of the vocational relevance. Okay, so this domain encapsulates the aspirations that all students will increase their economic productivity through the use of knowledge, understanding, and skills of the scientific literate person in their careers. So this is the one with the hope that if you go to science, you have a much more better economic standing. Okay, so this domain, it is expected that the chemistry education will enable students to be aware of opportunities for further study and chemistry related careers. So this is the one that will go to the field of science, or if we're talking about here specifically, the one that will go to chemistry. So these are the three domains of relevance as being related to the three main goals of education. Okay, so each aspect of this must be, we could say, included if you're going to teach chemistry. Okay, and each aspect would have different results depending on what the students really want. Okay, if he really wants to be in science, all aspects must be covered. Now, unfortunately, I told you the one that is questionable always here is this one. Okay, because what happened is whenever they take the course, what's the first thing the students ask? Whenever you ask them to take this particular course, are they relevant in my life? Okay, so that's already a challenge on the part of the teacher when student asks the relevance of that course to their life. Okay, now let's go to this notion of these so-called big ideas. Okay, why do we have this what we call big ideas? So when we talk about this concept of big ideas, central ideas, or great ideas, okay, so there are other what we call terms that is associated to this what we call big ideas. But if we're going to look at the big ideas here, big ideas, we could say, provides a conceptual lens for prioritizing content. Big ideas can refer to core concept, principles, theories, and processes that should serve as the focal point of curricula, instruction, and assessment. Okay, so when you look about the what we call big idea, it reflects the expert understanding and anchor the discourse, inquiries, discoveries, and arguments in the field of a study. They provide the basis for setting curriculum priorities to focus on the most meaningful content. They said the big ideas function like a conceptual velcro, okay, for a topic of study. They connect the discrete knowledge and skills to a larger intellectual frame and provide a bridge for linking specific facts and skills. Okay, a focus on these larger ideas helps students to see the purpose or relevance of content. Okay, so discrete facts we know do not transfer, but big ideas data are powerful because they embody transferable ideas. So most of the ideas that they have, they said the discrete facts, they do not transfer right away to the student. So by having these big ideas, okay, they embody some sort of transferable ideas applicable to other topics, inquiries, context, issues, and problems. Because we can never cover all the knowledge on a given topic. A focus on the big ideas help to manage the so-called information overload. So big ideas provide the conceptual thought lines that anchor a coherent curriculum. Big idea, we could say, is abstract. Its meaning is not always obvious to the students, and simply covering it will not ensure student understanding. Okay? Coverage is unlikely to cause genuine insight, but understanding must be earned. Okay? So the ideas must be uncovered and its meaning discovered, constructed, or informed by the learners with the aid of us teachers and well-designed learning experiment. So the concept of this big idea started maybe half a century ago. Okay? So big ideas, we could say, is not new. It started 50 years ago, okay, as policymakers in the education try to see how are we sure that students understand what we're teaching, okay? So among the three things that they look before they went to this so-called big ideas is the so-called curricular perspective. And in the curricular perspective that they have there, okay, this is just some sort of the introduction and elaboration of the big ideas in the chemistry. So the way that they do is, this perspective is your guide, okay, for you to teach the course. So in the chemistry, they have three main curricular perspectives. So the first perspective that they have is the fundamental chemistry. So this is the dominant characteristic here is the conception that chemistry is a conceptual and cumulative scientific system. Okay, so the curricular focus of fundamental chemistry is mainly learning to describe, explain, and predict chemistry phenomena. So you describe, explain, and predict the given phenomena. So that is your fundamental chemistry. Now, the other curricular perspective that they have is knowledge development in chemistry. So when you have this knowledge development in chemistry, the dominant characteristic here is the conception of chemistry as a scientific system that continuously develops through active participation of chemists. So what does it mean? Knowledge is growing, okay? It's not that you just said, okay, this is all about the chemistry thing. No, chemistry knowledge will expand as you continue doing experimentation, okay? So the curricular focus here is mainly learning how knowledge in chemistry is developed in socio-historical settings. What's the best example of this knowledge development? We go with the atomic theory. We start with John Dalton's concept of atomos, and then Thomson discovered that atom is just not what we call one big ball. It is made up of subatomic particle like element. And the billiard ball that John Dalton first proposed is now what we could replace by the plum pudding model. And then that plum pudding model was changed when Rutherford discovered that there's a nucleus that you have there. So from the plum pudding model, it became what we call the nuclear model. So that's the knowledge development of chemistry that you have in terms of the curricular perspective. Now, the last one that we have here is chemistry, technology, and society curriculum. So the dominant perspective here, the characteristic here is the conception that chemistry is a scientific system that plays an important role in technology and everyday life at the personal and societal level. So the curricular focus here is mainly on what? Learning chemistry concept and processes that are relevant to understanding the socio-scientific issue and context. Now, this curricular perspective, they can act both as a filter and frames for the big ideas, okay, that we're going to talk today. So, there are many, we could say, proposed big ideas. And the one that we're going to focus for today is the one that I sent to you, the readings that I sent to you. And the first thing that we will have is on Gillespie. So Gillespie Okay, he's a chemistry professor, a Canadian one, Ronald Gillespie. He asks the question, what must be in general chemistry? Or you as a teacher, you could ask, what are the materials that I need to teach? What are the topics that I need to include in a given course? Okay, so usually you ask the fundamental, what we call thing. Why do I need to teach this course? Why do I need to teach this topic? Why do I need to include this topic? Okay, so in a paper that he wrote 1997, he come up, okay, with 6 great ideas of chemistry. What I put here is just some sort of a statement from these 6 great ideas. So in his word, he said, this is the fundamental things that need to be included, okay, to appreciate chemistry, to understand and appreciate general chemistry. So the first statement that he had there is atoms, molecules, and ions are the basic components of matter. And if this is the idea that Gillespie forth, we could say the start of the atomic model starts with John Dalton. So he said modern chemistry starts with Dalton and the concept of atoms and molecules. Okay? So atoms is what? The fundamental unit of an element. Right? When you when one atom combines with another atom, just like hydrogen and oxygen combining to form water, you form a molecules. Okay? So molecules, we could say, is the basic component of compound. If this is the element, this is the basic component of the compound, specifically the molecular compound. Okay? Because you have ionic compound and they're not usually made up of molecules. The ionic compound is made up of ions. So that's the notion of Gillespie when he came up with this first great ideas. Atoms, molecules, and ions are the basic components of matter. So matter is just what? Everything around us, and it's made up of compounds and elements. Compounds mixing with another compound at variable composition will give you mixture. So that's the first idea of Gillespie. Now the second one, okay, chemical bonds. Okay, so if you're going to look at the word bond here, so we could say bond is the one that holds atoms together. So chemical bonds are formed by electrostatic attraction between positively charged cores and negatively charged valence electron. So the chemical bond is what atoms hold, what holds atoms together in molecules and ionic compounds. Now they said here, all chemical bonds are formed by electrostatic attractions between positively charged cores and negatively charged valence electrons. Electrostatic forces are the only important force in chemistry based on Gillespie idea. Okay? Another idea that he forth him as great is molecular shape and geometry. So here he said atoms in molecules and crystals arranged in a particular geometry. So he's just talking about the 3D geometry or 3D chemistry here. Okay, and the notion of geometry is usually new. It only happened what after Lewis proposed the Lewis structure, Gilbert Lewis. But if you're going to look about the confirmation for the geometry, it is just due to the instrument that were developed later, in the later half of the 20th century. Okay, X-ray crystallography, we could say. And I think the main model that he describes here is the BESPR, BSEPR. And then the fourth ideas that we have, atoms and molecules are in constant motion. So this is just kinetic molecular theory. Although this concept is introduced in what? In gases. To tell you frankly, the kinetic molecular theory can also explain, okay, the liquid and the solid structure. Okay. Now, the next ideas that we have here, atoms in molecules and crystal can reorganize to form new molecules and crystals. So this just pertains to what? Chemical reactions. So they said the development of new materials, okay, is possible because of chemical reaction.
I'll do it.
Okay. So in the chemical reaction, what happened? Okay, new products are formed when you react certain reactants. And the last great ideas of Gillespie, okay, is reactions occur when the disorder of the universe is increased. So if you're going to look at this disorder, so it just pertains to entropy. Okay? So what Gillespie tells us that any student taking general chemistry, okay, they should know these 6 fundamental ideas. Okay? He termed this as the 6 great ideas. He believed that every high school and college introductory course, chemistry course, should include these ideas, or the course should be built around them. Okay? Now, by the end of the session that we have here, one of the requirements that I will ask you to do is for you to put forth your own great ideas of chemistry. Okay? So the next one who proposed is what we call the great ideas is Peter Adkins. Now, if you are a chemistry major, you know Peter Adkins. Why? Because Peter Adkins is the author of most what we call physical chemistry books. Okay? So the original form of Peter Adkins' big chemistry ideas are this one. And I think I sent you a copy of this, what we call paper. Okay? But through time, there are some restructuring in the statement, but still, the concept of the great ideas is still the same. Okay, so before it says matter is atomic, and then it becomes matter is composed of atoms. Elements display periodicity, elements form families. Chemical bonds forms when electrons pair, so bonds form between atoms by sharing electron pairs. Molecular shape, so shape is of utmost importance. And there are residual forces between molecules. Molecules interact with one another. And then energy is conserved, is still the same. Energy tends to increase, okay? Energy and matter tends to disperse. And entropy tends to increase. So when you say disperse, usually entropy is the dispersal of energy. And then there are barriers to reactions. which is the same here. And there are only 4 fundamental types of what we call reactions. So let's try to discuss this one by one. Okay, so you can have an idea how you're going to do your own great ideas of chemistry. Because this came after Gillespie. Okay, and it's not surprising since he has what? He's teaching physical chemistry. Physical chemistry, Demos would tell you, that's the most fundamental chemistry. Okay? Demos will tell you that because Demos is a PChem. He's a PChem specialist. So let's try to look at Adkins' idea. Matter is composed of atoms. Okay? So we could say that's the currency of all chemical discourse. Even Richard Feynman once remarked that if there were to leave a message carved in stone that would put survivor of a nuclear holocaust on the fast track to our current scientific understanding, then he would scratch matter is atomic. Okay? Because if you're going to look at all matters, if you're going to look at its fundamental composition, it's made up of atoms. Okay? So whether it is a compound, if you break down the compound, okay, from molecules, the molecules will break down to give you atom. Now, elements form families. So this has something to do with what? The periodic table. Okay? In the periodic table, usually family, they have what? These are elements that has the same chemical and physical properties. And when you look at these properties, usually you will form periodicity. That's why you call it the periodic table, right? And then bonds form between atoms by sharing these so-called electron pairs, okay? So how do molecules form? How do ionic compounds form? Okay? So for molecules to form, they have to share electron. Okay? And when they share electron, they form a bond, which is your covalent bond, right? If there's a transfer of electron, they form an ionic bond. That's what it means here by what we call Adkins' great ideas. And I think it's similar to Gillespie ideas. And the same thing with the fourth one, shape is of utmost importance. Okay? Why is shape of utmost important? What can you say about H2O and CO2? They're both made up of what? 2 elements. Okay? A compound that is made up of one kind of element attached to 2 other kinds of elements. But how come they have different properties? What makes their properties different? Water is what? Polar, while CO2 is non-polar. Now, the main difference there is in terms of the shape that they have. Although they have the same number of what? Elements, okay? The way they have the shape is different. So if you're going to remember, this would have a shape like this. While this one would have a shape like this. So that's where the importance of molecular shape is being what we call applied. Molecules interact with one another. Okay? So what does this mean? Molecules interact with one another. Okay, so these are what we call when they interact with one another. So usually these interactions can result to the formation of condensed matter. And once we have here, okay, we will see the different properties. Okay, so how does solid, liquid, and gas differ from one another? It's just having something to do with the interaction that they have. Gas, they don't interact because they're far from one another. You put it with another gas, they're just going to be mixed, but there's no interaction. Liquid, what happened? They're close to one another, so they can form a condensed space. The same time with solid. Now, conservation of energy. So, what's the main reason why chemistry developed into a science? Okay, it's something to do with Antoine Lavoisier's discovery that in a chemical reaction, energy is conserved. Okay, if you're going to look at the definition of chemistry, usually we define it as what? Chemistry is the study of matter and the changes that it undergoes and the energy associated with it. Energy is always associated with chemical reaction. Okay, the endo and the exo thing that we're going to learn more later on. So, number 7, energy and the matter tend to disperse. So this is, we could say, if this is the basis of the first law of thermodynamics, this is the basis of the second law. So what happened? Tend to disperse. Okay? So the tendency is disorderliness. If you're going to look at the world around you, it's hard to have order compared to disorderliness. People tend to be what? Chaotic. So the same thing with energy and matter. Okay? They tend to disperse, or the entropy is high. So when entropy is high, there is a much high disorderliness. The 8th one here, there are barriers to reaction. So we could say the world is sinking into chaos, but the existence of barriers of reaction means that collapse does not occur in a flash. Okay? So there are barriers that will slow down reaction. And these barriers allow us to discover different way of fulfilling its destiny. Okay? So they said, how can you make money if you are in the industry? Okay? One way to make money in the industry is to make the reaction faster for the reaction that is slow at the present time, or to make the reaction slower for the reaction that is fast. So what does it mean? What's the main problem that we have here in New York City? The subway system, right? Why? Especially during the weekend. Why is MTA so slow? Because they have to replace some of the railings that they have. What's the problem with the railings? Just like any metal, they will undergo corrosion. Okay? So if you can prevent that from happening, you can make money out of it. What other aspect we can apply number 8? What if you can have a reaction that is faster? Okay? You can develop the so-called catalyst. So catalyst is anything that makes reaction faster. Okay? What if you can make your, what we call farm, your animal farms grow from, let's say, the 45 days in chicken, make it in what, 30 days ready for market? Okay? So chemistry can play a role there. So you can make the reaction there. So those are what means barriers to reaction. Okay? And there are only 4 fundamental types of reaction. And what are these 4? Okay? Acid-base is one of them. Redox is the other one. Okay? And then radical reactions. And then the Lewis acid-base reaction. So those are the 4 fundamental reactions that he listed. Now, as you know, this is just great ideas that's put forth by Peter Atkins. the ACS Exam Institute also introduced their so-called great ideas. And this is based on the concept of the ACCM, not ACCP. That's my mistake there. Okay. So what is this anchoring concept content map? So they said a limited number of anchoring concepts or big ideas would arise with the content of, within the content of chemistry. Okay. So the way that they look at this, they want to build the materials that is going to be taught in chemistry within the so-called big ideas. Okay, so they have their ACCM, what we call concept. So this anchoring concept provide the top level of a 4-level outline of the content. So as you're going to look at this, the first level is what? Anchoring concepts. And then the second level is enduring understandings. So level 2 of this outline includes foundational understanding of the anchoring concepts. So this is what you need for the undergraduate curriculum. So if you're going to go specific to subdiscipline, so what it tells us here is you can also include level 3 and level 4 in this level of ACCM depicting the consistency of the top 2 levels. So what's consistent here is these 2. Okay? And in the article that I sent you, these are just some of the great ideas introduced by the Exam Institute. So ACS Exam Institute, this is the one that do the exam. And I'm really lucky to be what we call included in some of the exams that they prepare. So here, matters consist of atoms with internal structure that dictate their behavior. So it's the same thing as Atkins and Gillespie. Atoms interact via electrostatic forces to form chemical bonds. And then chemical compounds have geometric structures that influence their chemical and physical behaviors. Intermolecular forces dictate the physical behavior of matter. And matter changes, forming products that have new chemical and physical properties. So as you could see here, it's just like they select some of the great ideas put forth by Gillespie and Atkins. Okay, so energy is the key currency of chemical reaction in molecular scale system as well as macroscopic system. Chemical changes have a time scale over which they occur. So this has something to do with the kinetics. Okay, all physical and chemical changes are in principle reversible and often reach a state of dynamic equilibrium. So I think this is the one that is new. Equilibrium. And then chemistry is generally advanced via experimental observation. So the example I have here is the atomic theory. It is possible, it's only possible for them to advance due to this so-called experimentation. And chemistry construct meaning interchangeably at the particulate and macroscopic levels. So these are just some, no, this is not some, these are the great ideas put forth by the ACS Exam Institute. Okay. Now, the last that I have here is the one put forth by Palanker, the one that I gave you. So this is what Palanker said as an alternative perspective. Okay. And if we're going to look at this, this is going to be similar to the last topic that we will have next week. So how did Palanker, Vicente Palanker from Arizona, put forth this what we call alternative perspective? So it still apply the what we call the great ideas or the central ideas. Okay, so here the query that they have is, what is the material made up of? So we could say that's the question of identity. How do we identify the chemical substances? So usually we characterize them, and then from them we try to determine the structure. So the structure and the characteristics that they have there, you have the so-called structure-property relationship. Once you have that, you can make new structure with the property that you want. Okay, the structure-property relationship. How do we predict the properties of substances? So that's how they do chemicals in the industry. That's how they prepare. Okay, so they identify certain parts of the chemical, and that certain parts of the chemical is responsible to a particular property. So what they do, they maintain that structure and put others, what we call structure, to enhance that property, like making it faster in terms of what we call experimental yield. Yeah. And then from that, they're going to analyze the reaction. Okay, chemical causality and mechanism. So why do chemical substance change, and how do chemical substances change? Or they can put a control on them. How do we control the changes the substance undergoes? So what does control mean? Do they want to make the reaction faster, or they want to make the reaction slower? Okay, and based from this, they're going to look at the benefits, cost, and risks of the material. So what will be the impact of the chemical action? Okay, so this has some input, we could say, from the industry. That's how they design molecules. Okay, that's how they design chemicals to use to solve a specific problem. Let's say to cure some diseases. Okay, sometimes they could start with what? Looking at some herbals or plant materials. So why do this particular plant used as a traditional remedy? So they try to find out what's the chemicals responsible for that. So instead of what? Harvesting a tons of material, so what they do, they just identify the structure that is responsible for that property and design it in the laboratory. Okay, so ACS also have these so-called big ideas for high school in chemistry. So they put 4 big ideas. Okay, so conservation of matter and energy, and I'm going to discuss in the next slide what are those topics included here. The behavior and properties of matter, and then the particulate nature of matter, and the equilibrium and driving forces. So as you could see, equilibrium still here. So I think that's the only one missing from the Gillespie and Adkins. Okay, but the ACS consistent on that. So when you say conservation of matter and energy, we could say this is the first law of thermodynamics. Atoms are not destroyed in chemical reactions, they are rearranged. It can also include forms of energy, and the energy changes in the chemical reaction. So we can include here stoichiometry and balancing chemical reaction. So in all of these aspects, there's a conservation of matter and energy. Okay, so that's one of the big ideas in the ACS recommendation for high school chemistry. Now the next big ideas that they have, the periodic table of elements as the master organizer of the chemistry. And then we have the gas law. And then how do we distinguish element, compounds, and mixture? I think it has something to do with what? The classification of matter. And then chemical bonding, the ionic and the covalent bond, and intermolecular forces. What differentiate gas from solids and liquids? Okay, so that's another what we call big ideas. Another big idea is that they have particulate nature of matter. So here we have the kinetic molecular theory, the structure of the atoms, ions, and the molecules. So how do we apply KMT to the three physical states? Because if you can remember, KMT was only described in gas. But as I told you, you can apply it to liquid and solid. And then equilibrium, the Chatterley's principle, the reaction rate, the thermodynamics, the entropy and the enthalpy, the acid-base reactions, the redox reaction. So these are the topics that is included in this what we call big ideas. This is the last one there, combustion. Okay, so these are, we could say, the big ideas that we have. So why did they put forward these big ideas? So they want it, like we say, as a starting point, and you build the other topics in these concepts. So we could say these big ideas, these are the one that in one way or another is related to things that people can see that is happening in the society, like the issue of this, what we call climate change. Okay, so I try to look at the DOE-NYC, what's the chemistry topics that they have. And in one article that I found out, these are the chemistry core topics. So the atomic concepts, periodic table, mole stoichiometry, chemical bonding, physical behavior of matter, the kinetics and the equilibrium, organic chemistry, redox, acid, base, and salts, and then nuclear chemistry. So what we're going to do in the next, in the remaining time, so I'm going to ask you to participate in the survey. What I'm going to do, slide by slide, I'm going to put, okay, the topic that we have here, and all you need to do is, what's the word associated with it? I just want to, my children just disturbed me, okay? So, are you ready? So I tried to see, I mean, you need to participate in the survey. So usually what will happen, you type a word that is associated in each of these ones. I'm going to go through this one by one. So just type a word that is associated when you have this atomic concept. So you just go to this side, pull
You're typing this in the chat box.
.com. No, here. You participate in the, what we call, not the chat box, okay? There's a site there that you need to go and type, at least for the atomic concepts. And then later on, we're going to discuss each of them. So I'm going to, maybe some tricks that I use when I discuss this concept that might be helpful to you when you teach chemistry to your students. So we go one by one, okay? And let's see. So you type words that is what we call, that comes to your mind when we say atomic concepts. I hope this worked. This is the first time that I did this.
So Professor, can you hear me? We're waiting for you to start the.
Okay, yeah, I'm trying to activate it now.
On there. That's right.
Like are you talking about like a free association of some kind?
Yeah, what's the word that comes to your mind when you heard this atomic concept?
Okay.
So you go to that folder and then type that word, because usually I never tried this, so I hope this works. One word is enough. Let's try this one. I want to see your input first, and then later on, I'm going to discuss to you the stuff that is associated here. And then this one. What comes to your mind when it is moles and stoichiometry?
Avogadro's constant.
Headache. How about this one? And then another one, kinetics and equilibrium. And I would suggest also that each of you type your name in the chat for my attendance, and then tell me what you're doing. If you're teaching chemistry, say you teach chemistry. If not, what you're doing, so I can at least make my lecture next time more general, to give me an idea on your background. Okay, so here's another what we call input of words, and then we go one by one, each of them, and then I'm going to input my own, we could say, stuff. At least this will be helpful for those who are really teaching chemistry. because I have the notion all of you are teaching chemistry. So my materials for today are really chemistry. So at least I can change some of the stuff that I have for next meeting. And then what do you hear when the word redox or oxidation reductions comes in? My worry now, if you're not in chemistry, how are you going to write the great ideas of chemistry on your own? Okay, so this one, acid, base, and salt. So we're almost done, and then I'm going to put my own input, or we could say crash course for you in chemistry. And I would say this will be very helpful for those who are teaching chemistry, because you can have the idea, use. pH, everyone, pH. Bitter salty. And last but not least, Yeah, living environments can be said as biology, because biology is the study of what? Living things. So I am become dead. Okay, so trying to go back in the previous slides that we have. Oh no. So let's try to see if the word that you have given is related to what the idea should be. So for instance, if it's atomic concept, okay, so what are the terms that you have there? So an atom is what? My pad is not on. So an atom will have electrons and then protons and neutrons, right? And then you can also include here the Dalton, which is usually like a billiard ball for the concept of atomos, which is just what we call borrowed from Democritus. And then from that concept, it becomes Thomson. Okay. What's Thomson's model is the plum pudding model, wherein he indirectly discovered the electrons, right? And then from that, Rutherford found out that the plum pudding model is not working because indirectly he found the nucleus, for which we have the nuclear model. So we could say that this two is in the nucleus. And this one is responsible for the mass of the atom, and this one's responsible for the volume of the atom. Now, from the plum pudding model, Rutherford developed the nuclear model because if the plum pudding model is going to work, okay, the alpha scattering that Rutherford threw to the gold foil, okay, will pass through. But based on the result, some of them deflected, some of them hit back, okay? But the nuclear model is not what? is still not useful because it cannot explain the line spectra. Okay, it cannot be explained by the what we call classical physics that they have before, why nucleus is stable. So from that, you have Bohr. What's Bohr model? The planetary model. Okay. Unfortunately, the planetary model only works for hydrogen. Okay. But it laid down the QMM model that we know right now about the atom. So what's the QMM? The quantum mechanical model. So there are what we call a lot of people involved here, but for most of this is Schrodinger and Heisenberg. So in the atomic concepts, you can also have the so-called quantum number. Okay. In the quantum number, you have the 4S there. The size, the shape, the spatial orientation, and the spin quantum number. And usually the first three tells you about the location of your electron in a given atom. So that's what we call the orbital. So this is, we could say, the atomic concepts that is involved. Okay. Now the next term that we have, periodic table. So I think the first word that should come in mind is the elements, because that's where the elements are in the periodic table. And then after that, you have the properties, right? The periodic table is what we call results, wherein they group the elements based on their properties. And out of these properties, you have the so-called the families. Okay. And then some of these properties, you will have atomic size, ionization energy, and out of this, you have the so-called trends in the periodic table. And you can also have words like metals, non-metals, and the semi-metals, or metalloids. So those are just some of the things that is associated with periodic table. Okay. I don't know how in-depth you are in discussing it in the high school level, but you could also include there the concept of what? The triads, the octaves, and then the personality that is involved, Mendeleev versus Mayer. So the triads, what they usually before, there's a guy who classified the elements known, and he found out there are some elements that has the same properties. When you group them together, they form into a triads. The middle element has the average of the atomic weight of the first and the third element. Okay. Now the octaves, on the other hand, I think it's Newlands. He tried to arrange the periodic tables in terms of properties, and he found out the eighth element has the same property as the first element. So he called it the law of octaves, just like the musical notes, right? The do, re, mi, fa, sol, la, ti, do. Okay, but the periodic table is given credit to Mendeleev, although Mayer is also studying the same periodic table during their time. Now the credit goes to Mendeleev because Mendeleev was able to predict properties of those elements that he said are not yet discovered but exist or existing during that time. And when they found out those elements, their properties are really close to those predicted by Dmitry Mendeleev. Okay, and Mendeleev also, if you have a periodic table, there's an anomaly between iodine and tellurium. Okay, so why iodine came after tellurium, although iodine has a lower atomic weight than tellurium. Okay, now Mendeleev based it on atomic weight, but if you're going to look at the periodic table right now, it is based on atomic number. So there's another guy responsible for that, a young Englishman by the name of Henry Moseley. He arranged the periodic table in terms of atomic number. And that solves the problem of iodine and tellurium. And atomic number is just, if you go to atomic concept, equals to the number of proton in a given element. I think that's the things that you should cover if you're talking about periodic table. Now for the moles and the stoichiometry here, okay, the most important concept here is the concept of mole. So try to think of it like a number that can be associated with dozen. So when you have a dozen, you have what? 12 items, right? But if you have a mole, that corresponds to your atomic mass or molar mass in terms of mass or Avogadro's number. So they said there are three ways to describe the amount of matter: mass, number of particles, and moles. So if we're going to look at this mole, number of particles, and mass. Now, how do you go from moles to mass? So usually you just multiply it with the molar mass. How do you go from mass to moles? You divide it with the molar mass. How do you go from moles to number of particles? You multiply it with Avogadro's number. If it's the other way around, you divide it with the Avogadro's number. So this is what we call the main issues of moles. Now, if you want to make it into stoichiometry, so you could just say mass of A, mole of A, number of particles A, and then you have what? Moles of B, mass of B, number of particles B. So you follow the same route as the one there, but you're now going to connect the two. And what will connect the two? This one. Based on stoichiometric ratio. Or the balance equation. Okay, so mole is a concept that when you say it, it represents a certain number. In terms of mass, that is equals to the molar mass. 1 mole is equals to the molar mass. Okay, so if you have water, 1 mole of water is equals to 18 grams of water. Where did I get the 18 grams of water? Okay. Where did I get the 18? I have 2 hydrogens. So if I'm going to look at the molar mass of hydrogen, that's 1 grams per mole. So 2 of them, that's 2, and then 16 from oxygen. So when I add all of the atoms there, I get 18 grams. And that also corresponds to the Avogadro's number, 6.02 times 10 to the 23 water molecules. So just like when you're asked a dozen, so a dozen would always be equals to 12. Now, the thing I show here is I can describe the amount, whether in mass, moles, or number of particles, depending what is given. So if I'm given the mass, I want to determine the moles, all I need is multiply it with the molar mass. Okay? Or no, from mass to moles, that's divided by the molar mass. If you're going to look at this arrow going there, that's from moles to mass, and this arrow going here, that's mass to moles. And in the stoichiometry, what I need is a balance equation. So I will know, okay, how many of a certain reagent would react with another reagent to produce a particular product. So that's the moles and stoichiometry. This is hard part because you have this calculation. But this is, we could say, the simplest way for me to describe moles and stoichiometry. So you just need to know what is a mole. What's the mole concept? So the best way to do it is when you are given a mole, that corresponds in mass to the molar mass of that given item, or that corresponds to a number that is the Avogadro's number. So that material has this 6.02 times 10 to the 23 molecules, or whatever is the units that you use there. Okay, so bonding, I would say covalent and ionic. So this is what? Electron shared. And this is electron loss or gain. Okay? You say bond, ionic bond, taken, not shared. Okay? So example that I can have here is maybe this one. Compared to this one. I would say this. Maybe I'll just use C. No, I can use F. No, F is not. Maybe Cl here instead of F. Because Cl would have so you have the Lewis dot symbol, which just represent what? The valence electron. So if you have sodium, you have it like that. So if you remove the electron, so you become Na+. Now your chlorine, it's in group 7, so it has 7 electron. If it gains 1 electron, it has a negative charge. I can put it. So that's what it means in a chemical bonding. Okay, so covalent bonding, ionic bonding. So this is what? Metals and non-metals. No, these are metals and metals, and this is metals and non-metals. And within metals, you have metallic bond. So that's chemical bonding. Kinetics and equilibrium, I just have, we could say 2 letters here. This is the small k, and this is the big K. So when you say kinetics, how fast or slow a reaction is. So you have here the rate, which is just equals to the concentration over time. So change of concentration over change in time. Now K on the other hand, equilibrium, So this is something to do with the ratio of the products times the products over the reactants times the reactants. So if you're going to do it like this, A plus B reacting with C plus D, so K would just be equals to the products now. This is crucial for other system of equilibrium. Another thing that you need to do here is this one. You can only achieve equilibrium if your reaction is reversible. So when we say reversible, okay, not one direction. Because the concepts of the reaction that we have is what? We have reactants here and products. But what will happen when you have a reversible, it now becomes double direction arrow. Okay? Now, organic chemistry, I think the thing that you need to be clear here, this is not, or you cannot define it as the study of carbon atoms, okay? Why? CO2, CO3, 2 minus, okay? They are not organic. But they have carbons. So organic chemistry, we could say, is the study of carbon with hydrogen usually, but not study of carbon atoms or carbon containing compounds exclusively. Because as I told you, this one, they contain carbons, but they are not organic. Okay, so usually most of the organic compounds, they contain hydrogen in addition to carbon. Okay, because I think some book would say exclusively study of carbon containing atoms, but carbon dioxide is a carbon, but it's not organic. It's an inorganic materials. Okay. Now redox. So it's just what? Loss of electron, or we could say electron transfer. That's the simplest word that you can say about redox reaction. And I usually ask my students to know this thing, Leora and Geroa. So what is Leora? Loss of electron. So if you lost an electrons, you undergo oxidation. And you serve as reducing agent. And if it's Geroa, you gain electron. You undergo reduction. And you serve as the oxidizing agent. So how do we have an example here like this one? Magnesium reacting with oxygen to give you MgO. Now, another thing that you need to know about redox is the so-called oxidation number. Why? Because by changing the oxidation number, that's the only way for you to know that there's a redox reaction. So oxidation number, you will assign this as 0 because they are elemental form. And here, this becomes what? Positive 2, and this becomes negative 2. And the way that you're going to look at this, okay, so magnesium is from 0 to negative 2. Oxygen from 0 to, oh, this is positive 2, negative 2. So what happened here? How did you become positive? Because you lose electron. So if you lose electron, you lose negative, so you become positive. So these undergo oxidation, lose electron, oxidation. And that is also your reducing agent. Why? Because it reduces the oxygen. So the oxygen, on the other again, undergo reduction because you gain 2 electrons. Why? You become positive. Okay, electron is the one that has a positive charge. So if you gain electron is the one that has a negative charge. So if you gain, okay, the species will become negatively what has a negative oxidation number. So it undergo reduction and it becomes the oxidizing agent because this oxygen will oxidize the magnesium. So that's the thing I think I need you to know about the redox reaction. Then acid, bases, and salts. So I like the one who says there pH, salty, bitter, and sour, bitter, and salty. Okay. So acid-base reaction, they're around us. So you're right, it's around the pH. So if you're going to look at the pH 7, so this is acidic. If it's less than 7, if it's more than 7, it's base. If it's what we call within 7, it's a salt. Okay. So another thing that you need to know is neutralization. And then you should also know about the strong acids and bases and weak acids and bases. So how do we describe strong and acid? Strong and weak? It has something to do with dissociation or ionization. Okay, if it's 100%, then that's strong. Less than 100%, it's weak. And usually they said it's easier to determine which are the strong one because if it's not strong, it is weak. So the strong acids that you have, usually you have 7 or the 6 in some book. So you have the HCl, HBr, HI, and then the oxo acid, nitric acid, sulfuric acid, and then perchloric acid. Now the 7th one in some book, they have chloric acid. So anything that's not there, it's weak. Now for the base, is the soluble hydroxides of group 1A and 2A. So there's sodium hydroxide, potassium hydroxide, lithium hydroxide, I think calcium hydroxide if it's soluble. So the rest are, we could say, weak. So that's the thing I can tell about acid, bases, and salt. Salt is the product of neutralization reaction. Now, nuclear chemistry, I could just say the reaction of the subatomic particle in the nucleus. So you can have here the bomb, the power plants, like Chernobyl. Okay, so the thing is, the nuclear chemistry is based on what? Einstein famous equation. Okay, so what does this E equals to mc squared means? That means you can top the mass as the source of the energy. So the masses pertain to the so-called mass defect. So what is this? What is this mass defect? So remember, you have the subatomic particle. So what Einstein said, if you're going to get the difference between the atomic weight minus the mass of all subatomic particles, there's the so-called mass defect. and you can tap it as source of energy. So whatever that mass defect, you multiply it with the speed of light, and it's going to give you energy. Okay? So we could say nuclear chemistry is a double-edged sword. It can give a lot of benefits to mankind, but it also has that phase that it can be destructive. So it's up for mankind how to tap it. Okay? So do you have any question? Now, the thing that I asked you for one of the requirements that you have on my part is you do your own big ideas of chemistry. So I'm just going to give you some of the stuff that mentioned here. So I hope it works. So I'll try to show here just an example. So this is nothing to do with the one that we have discussed, but it will be similar to that. So this is the example that I got from the internet. So maybe you can do a similar thing. The big idea of chemistry. So chemistry overlaps with all other sciences. And then the big idea that we have here, another idea is electron and structure of the atoms. So elements are composed of particles called atoms. Every atom has a nucleus and one or more electrons. Electrons determine the kinds of reactions that will happen. And then another big idea. So it's up to you to what we could suggest your own idea. There's no such thing as wrong answer here. But you just have to give a short explanation. Why do you think it's a big idea? So another big idea that was put here is most elements exist in chemical compounds made up of two or more elements. Bonds hold chemical compounds together. And then another idea is that reactants producing products. And then kinetic theory. All particles are constantly in motion. These motions can determine properties of a compound. And then the mole. So the mole is a unit that measure that chemists use. So it's 0.6.0 times 10 to the 23rd. That's the Avogadro's number. And then matter and energy. Every chemical process uses or produces energy often in the form of heat. Okay, so that's just one example. So another one that I have here. I hope this come out. So I just go right away to the concept that we had there. Here. So you just put this one. Chemistry as the central science, electrons and the structure of atoms, bonding and interaction, reaction, kinetic theory, the mole and the quantifying matter, matter and energy, and carbon chemistry. So it's up to you, but I want at least a short explanation on why you said that that's a big idea in chemistry. Now, my question is, what about if you're not chemistry? Because I have the notions that all of you are chemistry. Nobody told me from the education that not all of you are chemistry. Okay? So that's our first meeting. So we have 2 more meetings. So at least I hope you put your name there as my attendance record, because this thing is recorded. So I just can look at the chat messages that we have there. Okay. And at least I now know if you're not the chemistry, what's your background. So I'm going to incorporate it in our next lecture. So do you have any question? Although we are way above 12 o'clock already, this is the time
Professor,
to ask questions. Yeah.
question. So you're saying telling us to find a big idea. Is this like an assignment?
No, yeah, I mean, you create your own big ideas, just like Gillespie and Adkins. And you put the statement and then just put some short explanation. Why do you think it's a big idea? It's you designing it. Okay, if you want to teach your students, it's just like you're given a freeway. Okay, choose the topics that you think is a big idea. Let's say you have limited time to choose, especially let's say in the pandemic. Okay, so what are the stuff that you think is the big ideas that your students should know if they're taking chemistry?
Okay, so I guess I'm asking you, are we supposed to present it?
No, you're just going to write it, and that's one of the
Okay.
requirements that you have on my part. Because there's other two, every time we meet, I'll tell you the requirements that you have. So for this meeting, since we talk about big ideas, so I want you to write your own big ideas.
Okay, understood.
You don't need to present. All you need is you write it and then short explanation, and then that's the one that you're going to submit. And I'm going to give you the proper what we call the requirements paper maybe after we have the second meeting.
Okay, appreciate it. Thank you.
Yeah. Mhm.
And is this due by our next meeting?
No.
Okay.
No. It will be before what we call you end the thing. But I would suggest after we meet, you start doing now. You don't want everything to be at the end. I don't know how Demos, did you submit all the requirements with Demos? Because what happens is it might accumulate. So you don't want that to happen. So if you can start gathering the stuff now, and then just be ready, okay? But it will not be next meeting. All I can say is I'll give you ample time for that. But I just try it as early as now, since we discussed about big ideas and the requirements is you're going to do your own big ideas. So at least you have time to prepare already. Because what I've asked you, like next meeting, what I'm going to do, ask you is you're going to develop your own teaching material based on the strategies that I'm going to talk about next meeting. Okay? So do you have any question?
Just one more thing that you should know is that, as far as I know, as of yesterday, you guys still didn't have your course on Blackboard. So if you do ever want to...
Unfortunately, yeah, because it's easier for me to post the materials there. Yeah, because this is the last minute thing to tell you. They said, "Are we going to go or not?" And then when Dima said, "Yes, we're going." Okay, yeah. That's why I end up with three meetings compared to the usual 4, because I said I talk too fast. I might not have enough material to tackle for 4 meetings, because we are discussing. So you're going to be 4. I said I think 3 is enough for me. Yeah. But once we have that, because it's already approved, it's the higher ups that think. That's why sometimes there are still a lot of materials that I want to send to you, but some of them are so big because I what we call scan it. So when what we call Blackboard is available, I'm going to post all the materials. Okay, so I apologize for that. I was hoping that if it's my turn, we already have the Blackboard, but it didn't materialize yet. Okay.
It should be like 1 page about talking about our...
Yeah, I mean, usually like that. I'm going to discuss it specifically when I put the requirements to the thing. Because right now, just to tell you, I didn't realize that not all of you are chemistry. So if I already write the what we call the requirements there, then I have to modify it again. Because Demos doesn't care if you are in chemistry or not, because his topics are what? They're generalized, right? It's all about knowledge. But for me, they said, oh, you develop a material for chemistry teachers. So what will I do? I'm going to use materials in chemistry. And Demos didn't give me a notion that, hey, some of them are not chemistry. So right this morning, I could have included big ideas in science, because that's where the big ideas came from. It's not really from chemistry. Okay, it's all a big idea of science, and then what we do, the chemistry people, okay, since you have a big idea, so we will have our own big idea also in chemistry. If I have known that not all of you are in chemistry, I should have included the big ideas of science, but that's what I did. So I have to modify some of my notes for next meeting to include, let's say, some bio thing, not exclusive in chemistry, because we have limited. After this, 2 more meetings. So I hope you learned something. As I told you, this is my first time to have a course like this, so I'm still adjusting, okay? But what I try to share to you today is at least what is the most relevant things that you need to teach if you're teaching chemistry. Or maybe if you can apply it in your own science courses, then it's much better, okay? So question? So stay safe. We'll see each other again on Thursday. I'm going to send to you the Zoom details. Usually, if you don't see, if you don't get it tonight, someone emailed me. Sometimes I get so forgetful, and then I realize, oh, I never sent the stuff that is needed. That's the other part of not having a Blackboard, because in the Blackboard, I usually post the Zoom details in the announcement there. Okay, so I hope you learned something, and we will go on strategies in teaching chemistry and sciences next meeting. Okay, so good day to you. Although it's so hot right now, stay safe.
Thanks, Professor. Have a good day.
Thursday.
Professor?
Yep.
Yeah, sorry, I just came in really late. I was traveling out of town, but I was going to say that I'm a bio candidate. Yeah, just wanted to let you know that.
Yeah, so are you okay with, you can have a big ideas in biology if you want, if you're not what we call comfy with reading all the chem materials.
Hey, Professor, you said to type it into the chat box, right?
Yeah, biology preferred.
I mean, if you're not a chemistry, I'm open for you to do your own big ideas, whatever the field you would have. Because I know you have your own big ideas there.
Hey, Professor, you hear me?
Yeah, Luis, right?
Yes, yes. You said to type it in the chat box, right? What part or what subject area?
Yeah, if you're not in chemistry, you're free to do big ideas in your own field.
Okay, yeah. I put in I put it earlier when you first mentioned it. I typed it into the chat box, so it's in there. All right, you're saying that the big ideas can be related to our subject area.
Yeah, if you're not teaching chemistry, it's fine with me.
All right. And this is going to be available, the recording?
This will be available for recording, but the problem is we don't have the Blackboard yet. So I'll try to find ways where to put this thing.
All right. Sounds good. All right. Thank you, Professor.